Hey, we are back at Kroger's algorithm and quantum counting. So we were trying to figure out a trying to investigate and explore a bit more the fact that there's a relationship between the global phase of Grover's operator, so the Oracle and Grover's, that is actually proportional to the amount of solutions that there is in Grover's. And so we got to the point here where we saw that if so if I take a look, if I do a Hadamard gate and then I take a look at the probability of this qubit measuring one, that is, I mean, that is definitely proportional to these. But it's not that it's proportional. Is that there's a relationship between these and the number of elements that you have in here, that the oracle is flagging, right? This works, remember, because it's a Bloch sphere, and so if we have a plus state, right? So this means if I try to do a really primitive Bloch sphere, it means we are. So this is Z, this is X, and this is Y. Okay, so and here it means we're basically here, and so as we move along these x's, we will end up here. And so if you would end up here and apply Hadamard again, then so that's the minus state. It will take you to 1 with 100% certainty. If you stay in here, it's going to take us to 1 with 50% probability. Exactly, and so yeah, and so if I remember well, this means there are 5 solutions in here out of 5 solutions out of. Is it 5 solutions? 1, 2, 3, 4, 5. Yeah, 5 solutions. Out of 8 possible values, correct? No, but this is wrong. So this is what? That's okay. So this is 3 solutions exactly. Because yeah, I'm taking a look at the thumbnail. I'm taking a look at the small picture of the circuit here. This is 5 solutions, but you're missing here. You're missing the amplitude amplification. So this is 3 solutions exactly, and it takes us to 62.5%, right? And if we would have 4 solutions, that should take us to 50%, because I think that's the thing is, and then it will just bounce back. So it means really, was this what we? Oh yeah, so 5. Oh, wait a second. So you don't need to. So the global phase is just because of the oracle? Because here I definitely have 5 solutions, but I don't have, it's just the oracle that doesn't have amplitude amplification. So if I implement that here without amplitude amplification, what will happen? So let's try. So this is just okay. So this is 3. So this is these. A control Z, yeah, exactly. So these are the three solutions. If I make a gate out of these, so there's definitely two, and that is definitely three. I'll call this A3 or O31 because it's just the oracle. Okay, and I get rid of these. And I just add the oracle, so these instead of these. Okay, no, it's not true. Huh. So that was 37.5% versus the 60 to the 5%. Hmm. But then what? Or then here there's something wrong with. So A551. Can I take a look at these and I think it seems that I could. Okay, because this is VQ8, so I can actually fix that. See if I can copy these to AA51. So this is here. So if I do this, to work. Okay, yeah, it's appended that there. And O31, okay. So if I now use A51, so what do I get here? Okay, 37.5% of measuring one. So I think I did something. I don't think I did something right in the last video, because this is basically. Let me see if I can copy that. So it's just because I'm okay. So if I now do so I want to do 4 solutions. So 4 solutions basically means these, and then it means these. I'll just be structured. So this is 4 solutions. Make gate, and we'll call it AA41, and that should give us that should give us that should give us 50%, right? Yeah, 50%. But then it goes to 37% when you go to 5 solutions. Whereas 3 solutions is 62. Okay, we are at 5 already, so why not doing 6? 6, 7, and 8, right? And then let's see. And then let's see what happens. So what am I doing? So can I just, so I'll start with, so how do I do this fast? So I'll start with, so we've got 4 solutions. And then basically, yeah, so the easiest would be, so you've got 4 solutions, right? And then we can just replicate them, but having a 0 here. So why don't you, exactly. Exactly. And now 5 would be, so 4, 5, 6, 7, and 8, right? So we're gonna do kind of the same, but having this as 0 here. So of course that doesn't work. I'll now replace this one. This is this. This should be the Z, and here we should have exactly. And so the all zeros, you've got to basically negate everything, uncompute the negation, and then implement a all ones. Good. So now you've got all 8, and so we need 6, 7, and 8, right? So so this is 3, 4. This is 5, which we already have. This is 6. 8, 6. And this is A7. And this is A8. I didn't give it a name or what? I didn't give it a name. AA8. Okay. Gone. I could have probably done this programmatically with Cirq or Qiskit, actually. Because now what I want to do is I want to take a look and map all the numbers. So, and I should probably take note of those. Maybe I will open a Sheets new just to have that. Just to have that there. Okay, so we'll keep that sheet over here. Small enough that it doesn't bother us. Okay, perfect. So what about we start with, so we're gonna do 0, right? And then so this is the so the elements, and this is the global phase. So or it's kind of the probability of measuring 1, really. What I wanna, probability of 1 in the Z basis. So, and we wanna have, come on, 0, 1, 2, 3, 4, 5, 6, 7, 8. So with 0, we've got just the amplitude amplification, right? So there's nothing here that's been done. We've got amplitude amplification, and we've got a 100% probability of measuring 1. with 1, we've got an 0.875. With 2, we've got 0.75. With 3, we've got 0.62. 0.62. With 4, so we got 50%. Let's double check that. We should just do it like this, and then probably I'm better off. It bothers me to have to scroll all the time. I'm slow today. Exactly. So can I just move this? Perfect. 4, 5. With 5 is 0.375. Sorry, this is 5. So this is 5, and this is 0.5. With 6, we got 75 again. Yeah, okay, so it is. Okay, but that's funny. The 0 dot, this one is weird, right? The 5. Oh, again, sorry. Again, I forgot to add to all of those. The VQ8 at the end, sorry. That's bad here. So AA6, we get all the stuff here, and we add these. AA7. No, I hope I did not refresh. These 8. And I think 6, 7, and 8. Doesn't 8 have it? Didn't I add it? The 8 should be the last one. Here we go. Either here, but not here. Okay. So, and now, so we are at 6 is 0 to 25. Interesting. So this actually works. It goes all the way down to 0. 7. So 0.125, and 8 is going to be boom 0. So and if we, if you plot that, yeah, it's just a straight line. So basically, yeah, there's literally a proportion here. Now, so how does this translate to an actual phase, right? So this is basically, this is actually a phase of 180 degrees, right? And this is a phase of 90 degrees. Mm. And this is a phase of 0 degrees. And if everything in between is, let's say, proportional, right? So that would be, would it be 45 degrees? If it's 0.75, if I take a look at, so if I get into the plus state, I do a T-turn, I do a Hadamard gate. But this is, it's not 45 degrees. Because if I do this, then you got 50%. Exactly. So I thought a T-gate, I thought a T-gate would give you, what? So that's not, I'm lost right now. Okay, so I'm a bit confused right now. So, so that would be basically proportional, wouldn't it? Why it tells me 14% probability of measuring 1. Now I'm confused. If I apply a Hadamard here, this will end up there, which is a 14% chance of measuring 1. Okay. So if I apply a spinning Z, how does this look like? Seems like it's filled up. Doesn't this behave linearly? Shouldn't this be 45 degrees? And then if I do a 1/8, like if I do a 1/8, sorry, if I do so if I do 4/8, so that's 1/2, then it's 50%. If I do 2/8, okay. Okay, so it's not interesting. So it's not. It's really not a direct proportion. How can I know? Okay, so if I rotate, that's purely on the face. Oh, wait a second. Okay, but there's a global phase. 90 degrees all the time. That's 90 degrees. So my question is this on the, so this is not entirely on the y-axis. It also has a bit of a z-axis component. Oh, theta is 67%. 67%. Whatever that means. Now, how could I find intuitively what phase this translates to? So, for example, with AA2, or say with AA, with AA2, right? With AA2, we've got 75% chance of measuring 1. So how can I figure out what phase does this translate to? Okay, that's the next question to answer. Because I also want to, so intuitively, right? And then because you can't tell from the Bloch sphere, definitely you can't tell. You can't tell because there's entanglement. But you can definitely do it like this. So you can measure with a Hadamard, and then you could, like, honestly, you could do quantum counting like that without QPE. Because if you would sample that, then you know already. And yeah, you know already how to map to the number of flagged elements, so you don't really need to guess the phase. But would it be safe to know, for example, that let's take a look. So if this is a 90 degrees phase and it's 4 elements, right? So then you get these divided by these. So then it's a so then you're adding a 22.5 phase per element. Would that be correct? 22.5 phase per element. What happens if I rotate these 22.5%? So 0.225. Then I get 12% of measuring 1. Oh yeah, it's exactly okay. So so I could get in more precision in here probably. 90 divided by 4. So what if I say 90 divided by 4? Sorry. 4 divided by 90. Oh, what am I doing? 90 divided by 4. Divided by 100. Yeah, I mean, that's a 12%. It's an approximation. It's 22.5. So that will be these. And if I do these 5 times 2, okay, no, then it's not, doesn't seem to work. I mean, times 2, it's not times 2. What am I doing? What am I doing? So I'm at 180 degrees and I remove 22. So that should be these minus these, right? So that should be 157.5 degrees. Which is basically a is basically yeah, well, it's the same. 0.875. 0.875. Asian. It's not what I. That's exactly what I want to move away from. That's not. No, what am I doing? So it's 22. It's early in the morning. This is 22.5 increase of phase per exactly. No, but I was not that wrong. Okay, so no, but then I was right. Then I was right doing this minus these, so that would be the angle. But then that's not, as we've seen, that's not the case. So it's not that the so okay. So this tells me that the angle, the phase is not directly proportional to the number. But that was damn lucky. Then if I kind of identified this as being, so this is not directly proportional, but this is proportional. Hmm. But that's good. That confused me a little bit right now. I'm a bit shocked that the Hadamard gate does not give me that linearity, honestly. Mm, it should. Why shouldn't it? Anyway, so I shouldn't worry so much about that. Nevertheless, so it's not that the phase is directly. It has to be somehow. But then what's the relationship? Uh, uh, okay. This is because it's not the global, this is the relative phase. So, and we want to take a look at the global phase. So that's wrong. That's definitely wrong. Okay, but that global phase should be now in here. That's what I'm saying, right? So the phase kickback, the global phase should be applied, and these keep it as a relative phase. That's how I understand phase kickback. Okay, maybe let's go through the phase kickback. Let's try to go through a phase kickback chapter of Qiskit, the Qiskit textbook. There was a phase kickback. So is this gonna load or what? We're supposed to have interesting results. We have entitled to qubits by placing the control qubit in the state plus. Yeah, we see we have the CNOT acting on the state. Since CNOT swaps the amplitudes, we see no change. Okay, let's add a negative phase to the target qubit. If the CNOT acts on this state, we'll swap the amplitudes resulting in the state. This is interesting because it affects the state of the control qubit while leaving the state of the target qubit unchanged. Okay, but the phase we're moving the problem here, there's something off in here, which is there's something I don't like in this whole concept here, which is the fact that I see here this state is changed here. So right, that's not anymore the plus plus plus, and that's kind of against the definition in here, which is that state doesn't change, right? Only the control state qubit changes. Yeah, phase kickback. So it's very important is used in almost every corner. Where kickback is where the global phase added by a gate to a qubit is kicked. The global phase added by a gate to a qubit is kicked into a different qubit. Okay, so the global phase that this is added to that particular set of qubits, which varies definitely. Is then the one that's kicked back in here. So if you want to guess if you want to guess the global phase of that particular element, it's not that. So you should find a state that it's unchanged, and then you are going to know the exact phase. So, but then something's off with the quantum counting explanation in the Qiskit thing, is it? Keep back with the T-gate, yeah. So if I, by any chance, what happens if I do these? Then I get 25%. Which is these. If I put, for example, the 3 elements, 37.5, then I get these. Okay, so if I change that, the things flip around. Okay. Okay. guess just a technicality, but then I either read the quantum counting here in the wrong way, or because that's definitely affecting the state. So what we're seeing here, okay, so let's put it this way. So if we have 4, yeah, now the state is not changed. So now we're adding the maximum yeah. Okay, wait a second. I think I know where this is going. So amplitude amplification. So it's two things. It's the oracle and Grover, and it's the oracle and the amplitude amplification. So the amplitude amplification has a 90 degrees global phase to it, right? Because it takes me to 50% here, 90 degrees phase to it. Now, if you're when we're flying, so I think that I'm getting close to the answer. Why does this work, and why is this then proportional? Because if you're adding to amplitude amplification, if you're removing some of those elements, so the same, if I would just say amplitude amplification, right? Here you go. It's 180 degrees. It's 180 degrees. Global phase. And that doesn't change. It's 180 degrees. So, so by adding those oracles before the amplitude amplification, changing that, but it's still, if you would want to truly find the actual phase, you would have to change that initial state in here. But in this case, we don't care because it's not the phase that we want to find. We want to find, in this case, we're finding a proportion or a number that's then proportional to that. So I just got lost. We don't want to guess the global. I mean, I would, of course, I would like to I like to find the global phase, but actually I don't care because that global phase would still not tell me these directly. So this seems to be a bit more of a practical approach. Definitely. But then still, how would you find? Okay, done. I just got officially tired of these. So we've got these, which would kind of basically help us count. The how do we arrive to the actual global phase? That's an interesting question. What gate would I have to add in here? So now it's because again, that's kind of cheating because you're not finding the global phase of these, are you? Because if you're not changing these, you know what my point is? Is like if you go here, quantum counting, and covert cyclotron rotates the state vector by theta. The eigenvalues of the Grover iterator are these. Okay. And we can extract these using quantum phase estimation. Quantum phase estimation. Okay. So it's the, okay, so what they're saying is it turns out because this is this theta angle that you're rotating every time closer to the solution. It sucks that it's just given like that, right? The thing is, there's no point for me to try to arrive to that conclusion because I don't care about that theta. I don't care about that interpretation. All I care is about the phases and like trying to find a linear, trying to find a proportion between something I can measure in here and then the actual elements, and I just got it. So basically, with these approach, I would just isn't that even way cheaper than quantum phase estimation? If I would just well, of course, but if we would just sample this, if I would just sample the result of this, the measurement result of this qubit, then I can directly find the count the number of elements, and it allows me to count everything, even up to like to 8. Well, that's way better, I'd say, than the quantum counting algorithm. Does this work for higher numbers? We can take a look. I mean, I can try to do this with both Cirque and Qiskit next time and see if that I don't know, maybe nobody has thought of this before. I don't think so, but it's actually, so there seems to be a direct relationship between these and these, so we can definitely try that out next time. So that's going to be next video. We'll try to programmatically implement that and then scale it to different qubits and see if that works, see the efficiency, and maybe even I mean, real devices doesn't make sense, I guess. Okay, perfect.